Everybody, let's talk a little bit about thermodynamics, and let's go over question 19.43 in Braun-Lemay-Burston. Now, if you look at this question, okay, we're talking about entropy change. Remember, entropy is the randomness of a molecule, okay, or the randomness of a group of molecules. Okay, the more random something is, the more it's bouncing around, the more it's being crazy, the more likely it's going to have a higher entropy. Now, what we can do is we can make some assumptions about entropy in that gases have high entropy. Okay? And so I'm going to say that by saying have a high S. S is the symbol for entropy. Okay? And so if gases have a high entropy, actually, it's safe to say that most gases, their entropy is so high that it completely trumps anything else, any of the other states of matter. Okay? The next most random state of matter is an aqueous solution, and then then liquids, and then finally gases. So if we know that, what we can do is make some assumptions when we're given a reaction. So here we have nitrogen plus hydrogen gives us ammonia. And this is that reaction that I just ate, the Haber process, right? Where you're forming when you're making ammonia. And all we have to do really is compare. We have for part A, we have 4 moles of gas going to 2 moles of gas. Okay? And so 4 moles of gas is way more random than 2 moles of gas, okay? I mean, I say way, but it's definitely more random. I'm not comfortable saying it's twice as random, even though 4 is twice 2, because each individual molecule is going to have its own entropy. But we can still say that 4 moles of gas is way more random than 2 moles of gas. So the delta S in this case is negative because it's going from highly random to not as random. Okay? Now, for part B here has a solid. Solids are the least entropic, if that's an adjective, have the least entropy of all the states of matter. Okay? And so here's a solid, and here's a gas. And again, the gas is the state of matter that has the highest amount of entropy. So we're going from no moles of gas to 1 mole of gas. Okay, again, solids we're not going to count. Okay, so delta S in this case is positive. Okay, because we have 0 to 1, we're going up. Okay, now let's look at question C. Question C is 3 moles of gas going to 1 mole of gas. So even though that the number of molecules is the same and it's always balanced, let's just not get bogged down with some of the more complex things. Let's not overanalyze it here. The point is that you have 3 moles going to 1 mole, and so you have high random going to low random, so the change in entropy is going to be negative. And then D. Okay, now we have some solids and some gases, and some solids and some gases. Okay, and so, but again, we're just going to look at the gases. 3 moles going to 3 moles. Okay, now in this case, the delta S, the change in entropy, because it's 3 moles going to 3 moles, the change in entropy is going to be about 0. Okay, now we can't make any assumption here when it's the same number of moles. So that's something to keep in mind. Okay, when the moles of gas are the same, then there's no like second analysis or third analysis. We just say it's going to be about 0. Okay, we can then, if we really wanted to, we could then calculate using products minus the reactants the actual delta S and see what's going on. But that's for a different problem. Anyways, that goes over question 19.43. Have a great day.